What's up, everybody? On this video, we're going to talk about the processes of upwelling and downwelling. We have talked about them before when we talked about El Nino and La Nina, more specifically with upwelling. So now we're going to talk about it in a little bit deeper of a context. Um, and not just considering right along the coastlines, which is what we talked about when we talked about El Nino, right? If you remember with El Nino, there was a lack of upwelling happening because there wasn't this air movement over South America. And so then that's really bad for the local South American communities and economies. So when we're talking about these two processes, we're really getting into this idea of the continuity of flow. So we have to remember that the amount of water in the oceans, for all intents and purposes, is relatively fixed. So we're not considering sea level rise and the melting of our ice caps yet. So it's relatively fixed. Means that there's no change. There's not more of an influx than an outflux. There's not more of an outflux than an influx. It's relatively the same. And also, water cannot be moved from one location to another without movement of water between these two locations or between locations. So we're not playing Moses, we're not parting the Red Sea, none of that stuff is happening. We're keeping all physics that we know of good and kosher. So upwelling is really important because it delivers nutrients into an area, whereas downwelling is important because it delivers oxygen to the deeper oceans. So the reason how upwelling happens or coastal upwelling happens is basically you have this surface water divergence, which enables this cold, nutrient-rich, and oxygen-deprived waters to raise to the surface. So we see this a lot in the west coast of North America, especially off of the California coast. So we have winds that are blowing from Northern California to Southern California, because there's that big high, that Pacific high that's oftentimes parked off of our coast. So we have winds going from north to south. And because of Ekman flow and Ekman transport, which we talked about earlier, is there's this overall net transport of water off the coastlines. And when you're making water leave an area, again, you have to replace it with something else. That's that continuity of flow. The conservation of mass, basically. So when you are forcing water out of an area, you're replacing it, and what's being the replacement water is the cold, nutrient-rich water from the deeper oceans. And if we look at where these upwelling zones are, they really only make up about 1% of the ocean environments. But if we're to compare where these regions of upwelling are, and then compare where the world's kelp forests are, they're almost identical, right? So we go back to the previous one where we see this coastal upwelling occurring and where the kelp forests reside. So these kelp forests are really staying alive persistently throughout the year with the help and deliverance of all of this nutrients. And it's not just important for the kelp, it's important for all of the species of creatures that live within the kelp forests, and also the species that live on the surface water that don't necessarily rely on the kelp forests as well. And these are highly productive areas and highly productive marine habitats. And they're nurseries for a lot of fishies. Sea otters love them. Urchin love to eat them. We've talked about this relationship several times of how otters love to eat urchin and urchin love to eat kelp. So as long as there's enough sea otters to eat all the urchin, then we are doing all fine and dandy and groovy, right? But if we don't have enough sea otters to eat the urchin, then we have a huge influx of urchin, and they eat all the kelp, and then the kelp forests disappear, which is not great when you're trying to keep kelp forests alive, because they are very, very important for not only, being nurseries and homes for many different species, but they also provide us with a ton of oxygen as well. Now there's this process of downwelling, so it's basically the opposite. And there's two different kinds here. There's coastal upwelling here on the right, and then there's surface water downwelling over on the left. But basically, the coastal downwelling is the opposite of what we would see from for upwelling, right? So you have winds coming from the south to the north, and because of Ekman flow, you would have this influx of water towards the shore, and then that would be forced back down into the ocean, basically. Whereas sometimes we have this convergence of water. Generally, we would see this in like a hurricane sort of situation where you have all this water building up in the middle of the storm, or also in gyres, right? You have this buildup of water, and we don't have the physics on a planet where we just have like a shoot up of water, like a pillar of water. Like we're not the Bellagio in Vegas, right? We're not, Mother Nature doesn't play physics that way. And so the water has to go somewhere, and gravity is like, you're coming back down. And so it goes down into the oceans, and it delivers really important oxygen to those areas. So if we put all these ideas together of ocean temperature, ocean salinity, convergence, divergence, all of this stuff, we put it together, we can actually bring forth this idea of what we call the layered oceans. And that's what this particular map is trying to show. And the reason I wanted to leave this until after we went through upwelling and downwelling is because on this map it shows these regions of surface convergence and surface divergence, which can lead to either upwelling or downwelling, all in that same vein, same idea here. So in this, we're taking a slice of the Atlantic Ocean, and so we can see the North Atlantic deep water, some Antarctic bottom water, and some intermediate waters in here as well, and showing also the different salinities and temperatures for each water mass. So just want to do a brief review on currents here, where we have all of our gyres hanging out and doing their fun little thing. And so what I wanted to do now is talk a little bit more about these miniature circulations that actually exist within these major circulations. And maybe we've seen these before, especially if you're in my labs, you've definitely seen them, but they're called eddies. And these eddies are these pockets of moving water in this circular motion that can take energy with them. And that motion is away from the main flow, and also can gradually dissipate its energy through friction. And this is important because it helps mix and blend water. So what we see here on the right-hand side is a depiction of what the Gulf Stream looks like and some of the very prominent eddies that we see off of the Gulf Stream. So we have our main western boundary current here, right, of the Gulf Stream. And off of that, we have these warm water eddies, W for warm, and cool water eddies, C for cool. And how that happens is you basically have these two waterways that are kind of moving against each other, and that like cross movement creates these miniature circulations that then eventually break off and then create their own little circulations. It's actually a very neat little process. And this is what we would see in terms of like visually what we would see. So here's the east coast of North America. We have the Gulf current coming up here, and you can see these little eddies off of the actual current, like this little pool of cold water here and some pools of warm water. This is something similar in the Mediterranean, if I'm not mistaken. Back to this idea of convergence and divergence, but like on a very, very smaller scale. These are called Langmuir cells, and these are helixes or near-surface wind-driven water motion. So these are like baby waves or like baby circulations. Everything we've talked about before is like a global scale. This is like BB scale. So these cells in particular can extend downwind in order to form these windrows. That's not a typo, windrows of surface debris along these various convergences. And then we can see sinking material swept into zones of upwelling water. So basically you have, like I said, these little baby circulations, and then we can see kind of these little lines of foam and debris windrows in these regions of convergence. And then we have regions of upwelling, which would be divergence, but we can't see that part. And then just some kind of opposite little ideas here. And this is literally what it looks like. So maybe you've peered out into the ocean and you've seen something similar like this, and you're like, I wonder what that is. Well, guess what? Now you know. So that's pretty exciting, right? So the spacing of these can be anywhere from 5 to 50 meters. They can be closer together if the thermocline depth is really shallow. So remember that with the thermocline, there's not a lot of vertical mixing that happens. So because of that, then the circulations are much, much smaller, much more narrow. And the vertical extent of these can be anywhere from 4 to 10 meters, again, depending on the thermocline depth. And this helps mix the surface waters and distribute nutrients throughout. And we have these relative permanent convergent or divergent zones here, and that's what this map is trying to show, where we can have convergent zones near around 30 degrees north and south, which can mark the center of these large ocean gyres. And then these convergent zones near 50 degrees, which are regions of downwelling and low productivity. Productivity is basically like a lot of animal activity. And then upwelling associated with 3 major divergences, which delivers nutrients and supplies massive food chains. So that's what we would kind of see here in the tropical divergence regions, and even in the Antarctic divergence regions as well. And just a kind of reminder of what this upwelling and downwelling process looks like in a bit of a different way, I suppose. But it's still a pretty neat look, I think. On the left side, we have our cyclonic wind. So thinking of Ekman transport, right, we would have the water being kind of forced away. So we would have the process of upwelling. Whereas with anticyclonic wind, because of Ekman transport, we would have a convergence of water and thus downwelling. So if we were to look really quick, very last thing here at the upwelling and downwelling, we have the equatorial upwelling, which is most developed in the Pacific Ocean. And these positive values here indicate upwelling and negative values indicating downwelling. So we can see that there's the kind of like a little couplet here, right, of like this surface upwelling and the surface downwelling in this area for the month of July through this wind-induced upwelling in centimeters per day. Thank you so much for watching. Hopefully the audio worked.